Welcome, everyone. I am absolutely thrilled to be your expert math tutor today. Look, if you've ever stared down at a quadratic function graph on an exam paper and felt that immediate, horrible wave of panic wash over you, well, you are exactly in the right place. In this explainer, we're taking one of those really intimidating SPM-style questions and we are completely demystifying it. By the time we wrap up, you won't just know the answers, you're going to understand exactly how to pull them out with total confidence. We're taking that exam anxiety and turning it straight into an A-grade distinction. Let's get into it.
Okay, so let's dive right into diagram 13 from our source material. When you first glance at this, your brain probably screams, "Nope, it's a trap." But I want you to completely reframe how you look at this. This diagram is not trying to trick you. Think of it more like a beautifully designed escape room puzzle. It is literally packed with hidden clues. The text and the visual graph are basically talking to each other, and once you learn to speak their language, the answers just reveal themselves.
So here's our game plan for breaking this puzzle down today. 1. Unlocking the diagram. 2. Finding the axis of symmetry. 3. Finding constant m. 4. Calculating constant n. 5. Spotting common student traps. And finally, 6. A killer verification technique to guarantee your marks.
All right, kicking things off with part 1, unlocking diagram 13. This is all about translating those visual clues into pure mathematical certainty. Before we jump into any heavy calculations, we really need to understand what the question is handing us. Our source gives us a specific equation. F of x equals mx squared minus 8x plus n. I want you to think of this equation as the DNA of the curve. It dictates the graph's entire identity. Every single letter in there, the m, the x, the n, they all play a highly specific, non-negotiable role in determining exactly how that graph looks and where it sits. Our mission right now is to decode m and n.
Now, shift your focus to the physical shape of the graph itself. You see that smiling U shape? That curve swoops all the way down, hits a very specific bottom floor, and swoops right back up. That lowest floor is given to us as point W, sitting at the coordinates 4 and negative 25. That point W, that is our anchor. It's the key to almost everything we're about to solve.
Moving on to part 2, the axis of symmetry, or as I like to call it, finding the hidden mathematical mirror.
This is the very first question they hit us with. And to really grasp this, we need a simple analogy so you remember it forever. I want you to imagine a literal, invisible, vertical mirror. In math terms, this is our axis of symmetry. Because a parabola is perfectly 100% symmetrical, this invisible mirror cuts straight down through the graph, slicing it into two perfectly identical halves. And logically, to balance that curve, the mirror has to drop exactly through the absolute center, which is that minimum point W we just pointed out. So, the crucial clue is sitting right there. If the mirror drops straight down through the lowest point, and our lowest point is W at 4, negative 25, well then the mirror sits perfectly on the x-coordinate of that exact point. You see? The answer is literally staring us in the face. No complex formulas needed here. We just look at the x-axis alignment of point W.
Which means the answer to part 1 is simply x equals 4. Notice how we say that though? It's asking for the equation of a vertical line, so it has to be stated as an equation. X equals 4. Boom. That's your first mark secured, purely through visual logic.
Section 3, finding constant m. Let's see how the graph's smile actually reveals our hidden integer.
So the next part asks us to state the value of m. And this is brilliant because it perfectly illustrates what the coefficient m actually does. The m determines the total mood of your graph. If m is a positive number, greater than 0, the graph is happy. It forms a smiling U shape with a minimum point at the very bottom. But if m were to flip and become negative, less than 0, the graph flips too. It becomes a frowning N shape with a maximum peak at the top. Since our graph here is very clearly smiling, we absolutely know without a doubt that m has to be a positive number.
Let's build on that logic to get our final answer. The source text actually hands us a massive clue. It explicitly states that m is an integer between negative 2 and positive 2. Okay, so what integers strictly exist in that gap? Just 3. Negative 1, 0, and positive 1. Let's run a quick mental test. If m was negative 1, the graph would frown, so we eliminate it. If m was 0, the x squared term literally vanishes, meaning it's not even a quadratic function anymore, it'd just be a straight line, eliminated. That leaves us with exactly one option, positive 1, which perfectly aligns with our smiling, U-shaped graph. So purely by deduction, the value of m is 1. That's another mark in the bag. And guys, we haven't even touched a calculator yet. We're just reading the graph.
Section 4. Calculating constant n. Now we put the pieces together algebraically.
All right, here's where we shift gears from that visual logic into some methodical algebra. But real quick, what actually is n? In this format, that constant sitting all by itself at the end represents the y-intercept. It is the exact specific coordinate where our curve slices right through the vertical y-axis. So our job right now is to pinpoint that exact numerical value.
Let's walk through the substitution. Step 1. We rewrite our DNA equation using the m we literally just found. Since m is 1, our function cleans up to f of x equals x squared minus 8x plus n. Step 2. We need to feed this equation some solid data. The absolute best data we have is that minimum point w at 4, negative 25. This tells us that whenever x is exactly 4, the entire function's outcome, the f of x, is negative 25. Step 3, we plug those in. We get negative 25 equals 4 squared minus 8 times 4 plus n. Simplify that down. Negative 25 equals 16 minus 32 plus n. Well, 16 minus 32 is negative 16. Toss that negative 16 over to the other side by adding it to our negative 25, and
We get negative 9. The constant n equals negative 9, meaning our graph crosses the y-axis right at the negative 9 mark. And just like that, we have fully solved the entire 3-part question.
Section 5. Common student traps. Seriously, do not lose easy marks here.
Listen, our lesson isn't quite over. As your tutor, I need you to add these classic mistakes to your quick revision checklist because I see students stumble over these all the time. First trap. When asked for the equation of the axis of symmetry, people just write the number 4. Nope, a single number isn't an equation. You have to write x equals 4 or you lose the mark. Second trap. When plugging in point w, students get rushed and swap the x and y values, putting negative 25 where the x should be. Always remember, x is the first number in the bracket. Finally, ignoring the constraints. People try to blindly guess m without noticing the text explicitly locked m between negative 2 and 2. You've got to read the whole puzzle, guys, not just stare at the picture.
And finally, Section 6. Answer verification technique. How to actually guarantee that A grade. Honestly, this is my absolute favorite part because it puts the power entirely in your hands. This is how you act as your own exam grader before you even hand the paper in. We deduced that m is 1 and n is negative 9, right? So, step 1. Build the complete fully formed equation. F of x equals x squared minus 8x minus 9. Step 2. Grab your scientific calculator. Type out that exact equation, but substitute the x with the number 4 from our minimum point. Step 3. Hit equals. If your math is flawless, the calculator will spit out the exact y-coordinate of point w. It should say negative 25. If it does, you are 100% verified. You've basically reverse engineered the entire puzzle to prove yourself right.
So I want to leave you with a thought to take into your weekly study plan. When you stop viewing math as a series of stressful traps and start translating those visual clues, like the smile of a parabola or the exact coordinates of a minimum point, into hard algebraic facts, isn't every complex quadratic graph really just a puzzle waiting to be solved? My challenge to you this week: test this visual translation logic out yourself. Do progressive drills. Start with level 1 basics, just finding the minimum point. Move to level 2, finding constants from y-intercepts. Then push yourself to level 3, tackling HOTS problem-solving questions. And always use your verification techniques to check your work. Keep grinding, keep learning, and I'll see you in the next explainer.